So Eli, who goes by the pronouns they, them, is a lead data scientist at Tempest Labs in Chicago, where they build tooling to deliver oncology data to clients. They've previously worked on distributed modeling, ad spend optimization, and large-scale survey data analysis. They hold a PhD in ecology and evolution from the University of Chicago. And Eli is going to talk about how to think like Git.
So my name's Eli Sander. I'm the lead data scientist at Tempest Labs. And just to give like a quick one-sentence pitch, Tempest is hiring for lots of different positions. So if you're interested in solving difficult problems in precision medicine with data and AI, come check us out. And today I'm going to talk about how to think like Git. If my slides will advance. Okay. So I wanted to just motivate this by talking about some times that Git has made my day really difficult. I've definitely not always been very good at it. So there was one time, my first internship out of grad school, I spent hours working on a rebase that I ended up pulling in a coworker, and like he had to spend forever helping me out. And I felt really bad about how much of his time I took up. He was very nice to me. Even worse is the time that I was in grad school and I pushed so much simulated data to Bitbucket, which is a lot like GitHub if you haven't used it. They locked my account and wouldn't let me push anything else. And I thought I wouldn't be able to like access my dissertation anymore. And then there's just all of the times that I hit some kind of merge conflict and just panicked and like deleted the whole repo and started over. So if any of these situations sounds familiar to you, you're not alone. Git can feel really like a black box and pretty scary sometimes, but it doesn't have to be this way. And what I want to do is help you understand Git a little bit better so that you can have a mental model for what might be happening. So that you can debug it like you would debug your Python code or any other code that you're writing. So magic school bus style, we're going to go inside Git's brain and try to understand how it thinks. So my agenda is first, we're going to design our own version control system from scratch. Then we're going to learn how Git works. And then we're going to use that understanding to solve all of our Git problems. Should be pretty easy, right? We got plenty of time for that. So first, starting from scratch, let's build a version control system. And before I do this, I just want to take a second and talk about why this section is in my talk. So we could start by just talking about how Git does things, but I think actually spending some time starting from like not having any version control system, what are the problems we need to solve and how might we solve them, really gives a lot of insight into why Git is doing what it's doing. I actually did this exercise for a few hours in a big pair programming project, and I didn't get very far. It was really frustrating, and I felt like I did a really bad job at it, but I'm so glad I did it because I learned a ton about version control and why it works and what it's doing. So let's start with a really basic problem. If we have no version control system and we want to make a change to our code, what do? So probably you've done something like, you make a change to your code and then you rename it like script 3 final. That happens because you don't have a good way to checkpoint your code. So if you need to like create these little like save points or checkpoints in your code, it makes it a lot easier to have that security that you can go back and revert something if it's causing problems for you. So we're looking at it from the perspective of building our own version control system, right? So let's do just like the most basic thing we can and just save a whole new copy of the code every time. So you have some repo, which is a folder, which may have other folders in it, some files that have code, other things. We're just going to take that whole folder and save it somewhere else on the computer. And let's say we're going to stash it in like a version control folder that the user doesn't see. The user doesn't need to know how we're storing it or where. This is just for us to be able to like access it when the user wants to get their code back. And then we need to name these checkpoints somehow. Just for simplicity, let's just like have an incrementing number. So then it's kind of like a built-in time record because commit 1 comes after commit, or comes before commit 2 and so on. So here's an example of what our little like version control system looks like right now. So we've got this VC folder, which is short for version control. And let's say all of our repository history is going in there. Then when the user makes a commit, and I'm going to use kind of this Git language throughout, just because I'm assuming that's familiar to everyone watching this talk. So if you run VC commit, let's say that's our little command line command that we run, then we create this checkpoint folder 1, and we save everything in the repository, in this case, test.py. Then we make some changes, we add another file, checkpoint it again, and then we get folder 2, and we have what I'm calling test.py prime, an updated version of that file, and then another file in there. So that's just an example of how we'll store it. So this seems really inefficient, right? If your repository is big, it's going to take up a ton of space. So let's just solve that for now by zipping the entire folder. We just compress the whole folder and move on. That's good enough for now. So problem 2, we want to experiment. So let's say, I'm working from my checkpoint 2, and there's a couple different things I'm working on at once. I want to build this new feature, but it's big. It takes a lot of time to build. But then I also have this bug that I need to fix, and I don't want to get the code mixed up between those two things. And I'm calling these different kinds of changes experiments because maybe we want to keep them and maybe we want to get rid of them. But then we need some concept of branches in Git language. So this suggests a kind of tree structure, right, that we need to be able to split. We don't just have this linear history anymore. So my suggestion is we store this tree structure in its own file. So now in my VC folder, let's say we added more commits to the history, right? We have 6 different commits, and they're meant to replicate this tree structure that I'm showing on the right here. So we have these 2 different branches or experiments. One has commits 3 and 5, and one has 4 and 6. And again, those numbers are just based on at what time did we make that commit. And then we want to store the structure of this tree itself in this little tree.txt file. And maybe a way that we can store that is we just append the parent commit and the most recent commit to that file every time we make a commit. So I'm using Airflow-ish syntax here with the bit shift operator, but I'm just saying commit 1 points to 2, 2 points to 3, and so on. So this is okay, but it's sort of hard to keep track of what an entire branch is. You have to know what the most recent commit on that branch is to move back and forth between them. So we can keep things more organized by letting the user name their branches. Maybe the user chooses to name them main and dev, and then we can just append the most recent commit onto that branch history. So in this case, we just have the whole history for main, and then that dev branch, we show where it splits off. It splits off at 2, and any commits that we add onto that. And then the final problem I'm going to solve in this little mini version control system is being able to combine code from different branches. So let's say we've been working on our big feature for a while, and we want to bring it in from dev to main. So this is a merge, right? Let's say in our system, a merge is just another commit. We don't actually differentiate it at all. But the only difference is we have the history of all of the changes from that branch. So we need some way to identify and resolve any conflicts that happen between those 2 code sets. So what I'm going to suggest is that we compare files using the SHA-1 hash. And what a hash function is, if you're not familiar, is it's a function that takes in the variable length, like a file or some code, whatever, and it produces a fixed length character string. And if it takes in exactly the same text, it'll produce the same hash. So we know for sure if we get the same hash for 2 different files, those files are the same. And this is really helpful because it means we can just accept any files where the hashes match, and then we can just flag to the user any files that have different hashes. So we'll just tell the user, hey, here's the files that have some mismatch. You need to resolve the conflicts between them. And just one thing I want to highlight here is that this idea of a merge is directional. So when you're merging A into B, you're adding a commit onto branch B, right? So that's a different commit history than if you're adding B into A. And just to show what that looks like in our little tree structure, so let's say we want to pull everything from that dev branch into main. In that case, we're just adding a commit number 7 onto main. This is what it looks like in our history. The user maybe has to go through the effort of figuring out how to resolve some conflicts, but as far as what we're storing in our system, it's just another commit. Great, so now we have built a really simple, basic version control system. Let's see how Git does it. So a confession for anyone who read my abstract, I mentioned something about hand-drawn animation. I actually, when I wrote my proposal, was under the impression that Git stores the changes between commits in each commit that it makes. And so I had this whole analogy planned of these animation cells that you layer on top of each other. I thought it was really clever. But when I actually did the research for the talk, I realized this is the way that a lot of version control systems work, but it's not how Git works. And Git is actually a lot simpler than this. Sorry if I misled you into coming to this talk, but I learned a lot about Git writing it, so that's very exciting for me. So it actually turns out that Git does what we did, which is kind of wild to me. It stores every file every time you commit, the whole repo essentially. So that means that every committed version of every file is stored in the .git folder, and the .git folder is just the equivalent of our VC folder. It stores the repository history for a repo. So every file in its entirety is stored there, which seems wildly inefficient at first glance, but it works really well, actually. The simplicity of it, it's pretty powerful. So let's talk about how Git does checkpointing. So obviously these are commits. So what Git does when you run git commit is it compresses using zlib, which is an open source compression library, and hashes using the SHA-1 hash every file in the repository. And then the folder structure of your repository is encoded in a bunch of tree objects. And a tree is essentially a manifest. So it lists out all of the files and folders that are in the repo, and basically has pointers to the hashes. And those tree objects are just in files. It compresses them and it hashes them. And then it makes a commit object, and that's a file that lists the hash of the tree and the hash of the parent commit, and then along with some user info and a commit message. And then that's just a file, right? So it compresses that and it hashes that. And those all go in the same place. So everything lives in this .git folder, and then there's a subfolder called objects. So files, commits, trees, all of that compressed hash lives in that folder all together. And every object, this is actually really clever, really simple and clever, is named after its hash. So that means that no objects are duplicated, because when you make a commit, if you haven't changed a file, it's going to have the same hash. So that means that file name already exists. So we'll just overwrite it. And just a side note, sometimes people worry about what if you hash two different files and you get the same hash? This is called a hash collision. These are basically impossible. This is so unlikely to happen that it's just not worth worrying about at all. So let's actually look at some of these objects. So what's in a commit? So you can see this first line here, this tree object. There's a bunch of random characters and numbers. This is the hash for that tree object. And then that hash next to the word parent is the hash of the parent. So these are also the file names, right? So now we know where to find them. Then it says that I'm the author and the committer, and my commit message is a test for the PyData talk. And now this is actually the tree object. If we look at that, if we go to that file, that tree hash. So right now we're looking at my website, actually. So my website's a GitHub Pages website. So it's all in a repo. So this tree object, you can see there's a bunch of hashes here, and there's things that say like blob and tree. So blobs are essentially files. So this blob with the hash at the top is my .git ignore. If you find that hash and like uncompress the file, you can see what's in my git ignore. And then those trees are basically like hashes for another tree object, and that's like a folder. So it'll list, if you go into that tree object, everything that's in my underscore data folder, for example. Yeah, so that's what's in commits and trees. So let's talk about how we branch, like how we run experiments. So branch information is stored in .git/refs/heads. So here I've listed out everything that's in that folder. You can see there's 2 files. So I have a master branch and a test dev branch. And if you just print out what's in one of those files, it is just a hash. And that hash is a commit object, and it's the commit, the most recent commit on that branch. And this is basically it. The entire tree structure isn't stored anywhere in a file the way that we did. Basically, you can go back in the Git history by looking at the parent commit in this commit object and the parent of that commit. And so like working backwards that way, you can get the entire tree history. So like we did, it lets users create named branches and they just track the head of each branch. And one thing I want to point out is that there's no canonical branch. The naming conventions of like master or main are just naming conventions. So all branches are the same as far as Git is concerned. So finally, how do we do merges? This is actually quite similar to what we did in our little simple example. So it's got these tree objects, right, that gives a listing of all the files. And so we can compare everything in the 2 trees. And then any new files that are in one tree or the other, we can just accept those changes in from either branch. So there's no conflicts there. We just bring those all in. And then if the files have the same name, check the hash. And if the hash is matched, then like we did, we know the files are the same. So we don't have any conflict. If the hashes are different, then that means there's been some change on at least one of the branches. So we need to go into the file to understand what's going on. And then we follow basically the same process, just at the file level rather than at the tree level. So we compare everything in the 2 files, find the most recent common ancestor of the file. And we can do this by going back in the Git history and looking at the hash of this file at each time point until you find like matching hashes essentially. So once we know what that common ancestor is, we can accept any unique changes from either file. So if a line is changed on branch A, but not on branch B, then we accept that change in, or if there's a new line rather. So otherwise, if there's been changes on both, then Git doesn't know what to do. It has to raise a merge conflict. And basically what that's saying is there's something going on here that a user needs to look at and just confirm what's the actual correct thing to do. So now we have some basic understanding of how Git does things. So let's talk about how this works in practice and how we can use it to understand how our workflows work in practice. So I've made this goofy GRU meme. Basically what I want to point out here is Git doesn't care about what you have in your local copy or what I call the working copy. It only cares about what's in the .git folder. So the .git folder, that's all Git knows about. Local changes that you make don't affect your Git history. So you can make changes to all kinds of files. If they're not committed, they don't exist as far as Git is concerned, which is great. You can make lots of changes and experiment and try things out, and it doesn't get stored in your history. But this can have some surprising consequences for people who aren't used to this paradigm. So again, the copy that you're looking at when you have it in front of you on the computer, that's your working copy. Git doesn't know about anything that you haven't staged or committed. And what that means is if you are on one branch and then you check out a different commit or a different branch, it doesn't touch those local changes. So if you are starting to work on a bug fix, but you don't commit those work in progress changes, and then you switch back to main, those changes will follow you and you'll have that like partial bug fix in your working copy. which can be a little surprising to people sometimes. Yeah, so uncommitted changes follow you from branch to branch. And if you check out a commit that conflicts with your working copy, Git doesn't know what to do because it doesn't have the hashes, it doesn't have the tree objects, it doesn't try to resolve it. It just says, nope, this is on you. You have to like either get rid of these changes or commit them or do something because I don't know how to fix this problem. So the take homes here, before you commit or check out your code, always run a git status, because if you have forgotten that you like made some changes, you might get unexpected results. So it's always good to run a git status just to make sure everything is as expected. And then also, if you have some work in progress changes and you want to switch branches, it's a really good idea to commit them, even if they're not done. You can mark them as work in progress or whatever you want, but it's really useful to commit them so that they don't follow you to the next branch. So next, I want to talk about fetching and remotes. You may have seen this meme before. There's no cloud, it's just someone else's computer. So remotes work like this too. And remotes are, if this term isn't familiar, this is basically any other copy of the Git repository that's on anyone else's computer. So GitHub is a remote, or your like coworker's computer that has a copy of the repo, that's also a remote. There is no remote, it's just someone else's .git folder. So this kind of blew my mind when I realized this. Running git fetch is actually like exactly the same as if your coworker emails you their .git folder and you copy it into yours. That's all it's doing. It's just getting the .git folder and just plopping it in yours. It's just that setting a remote is more convenient than email. Like doing all of this via email seems very error prone and annoying. And it all feels very official, right? Because there's this command line interface with all these things you have to learn, and you're supposed to name your like GitHub remote upstream or like origin, and that makes it seem really fancy, but it's like not actually that fancy. Again, it's just emailing you the .git folder essentially. So let's talk about GitHub, and this applies equally to any other hosting service like Bitbucket or GitLab. Basically, GitHub is just any other working copy. So at its core, there's a really nice UI that's just a wrapper around the Git command line interface, which is great because the Git command line interface is like the most complicated part of Git. It's really easy to get overwhelmed by that command line interface. And so GitHub makes it a lot friendlier for people who are trying to like get started using version control and understand what's happening. Of course, there's some added conveniences. Right, Git doesn't have this idea of like a canonical or default branch, and GitHub lets you set that so that if you go to the repository, by default, it's going to show you that default branch. So that's why if you go into a repo at work, maybe it'll show you like main or master. And GitHub has added these features over time that let you edit from within GitHub, and that lets you treat it like a real working copy. So you can actually make commits within GitHub. That's because it is a real working copy. GitHub also gives better user visibility at the user level, so you can see what are all of the repositories that this person has contributed to, things like that. And then there's also like organization level, like concepts, and permissioning adds more security. So there's lots of great reasons to use GitHub. It's very useful, but fundamentally it's another working copy. So just a few final thoughts to wrap up. So again, Git is a really complicated command line interface, and I think that is what people think of as Git. And so it feels very overwhelming and scary. But actually, the tool itself is really simple. It's just like compressing and hashing everything and just chucking it into one folder. It's like deceptively simple. So what I want to encourage you to do is when you run into an error or a conflict and you like start to panic, don't do what I did and just like delete your entire repo. Just take a step back and look at it from Git's perspective. So take a second to think about like what is in my .git folder right now? What's in my working copy? And is that different than what is in the .git folder? And then if you're trying to pull and you get some kind of error when you're trying to run a git pull or a git fetch. What's in the remote? How might that be different from my .git? How's that different from my working copy? And how is like the differences between these things, like how could that be sort of creating the error that I'm seeing? And I also want to make a pitch for spending a couple hours being frustrated trying to build Git from scratch. So if you try to build your own version control system, it's going to give you a lot of information about how it works, why it works, what's hard about it. It doesn't need to be something that you're going to use. You can build it in Python, you can do whatever, but it's a really interesting and useful exercise. So that's pretty much it. I want to leave you with a few resources, and I'll post these slides on my website. So Git is simpler than you think is an article that I referenced really heavily when I was writing this talk. It really goes into the Git internals at a really understandable level, and it's a pretty quick read. Git internals is an online resource. It's really in the weeds, but it's kind of like a useful reference. So I did some of my like fact checking using that. And then I also have to make a quick pitch for the Recurse Center, which is sort of like a writer's retreat for programmers. It's all virtual right now, but when I went, it's like you go in person into like a big room for a few months and collaborate with people on whatever you want. And that's where I did that original exercise to try to build version control in Python from scratch. So if you have the opportunity to go to the Recurse Center or a program like that, it's a great way to really learn about this stuff. And that is it for me. So with that, I'm happy to take any questions.
Thank you so much, Eli. This is really exciting stuff. My mind is blown. I for sure learned something. And EL has a question. We have about 2 minutes left. What is the difference between git fetch and git pull?
Yeah, great question. So git fetch just does the like emailing into your .git folder thing. So it doesn't affect, it doesn't do a merge into your branch. It just like pulls those objects into your .git. So I believe that git pull is actually just a wrapper around running git fetch and then git merge or something along those lines.
Awesome. Hey, thank you so much for your talk, and thank you.
Thanks, everyone.